Delighted. For a while, I'll be here almost for the whole month of September. So if you want to chat after the seminar, I have a very large window open. Um, so yeah, as Gregor said, I'm from IJC Lab in France, and I'll talk to you about ab initio nuclear properties from low-resolution chiral interactions. So whoop. Is it there? Yep. Yeah. Wait, where am I? Okay. Yep. Let's get that out of the way. So yeah, to introduce briefly IJC Lab to the people who don't know it. So it's a research lab in France. You see downtown Paris, Eiffel Tower for reference. If you come visit us, usually you land at Charles de Gaulle Airport, northeast. You cross the whole area and you get this southwest of Paris, and that is like the nuclear physics area around Paris. So you have CA Paris-Saclay here, where I did my PhD, and IJC Lab here in Orsay, down in the valley. Which you might not know because it's fairly recent. It was created in 2020, but it's actually the merging of 5 historical labs that it's actually mostly young people here, but the least young people in the audience might know about. So IPN, which was the big nuclear physics lab in the area, and then particle physics lab, material sciences lab, theoretical physics, cancer research. And so we are hosted on the campus of Université Paris-Saclay, a bit like EFRIB here on MSU campus. So that's for the geographical situation. But now in terms of research, so I do low energy ab initio nuclear theory. We'll come to the ab initio in a second, but low energy nuclear theory, what does that mean? I see nuclei as A-body systems with Z protons and neutrons. On this beautiful nuclear chart here, you have the number of protons on the y-axis, neutrons on the x-axis. You see a bunch of yellow squares. Those are isotopes that have been observed. The black squares correspond to nuclei that are stable. And then you have grayish, greenish lines with specific numbers yet that you might not be able to read. Those are what we call magic numbers. That is specific numbers of protons or neutrons for which nuclei exhibit a particularly high stability with respect to their neighbor. So that's our ground play in a sense, and we try to answer a bunch of questions. How many of these nuclei do exist? What is the heaviest element? What is the limit here? What are those magic numbers? They are not trivial, and actually they tend to change if you move away from those black squares, which we call the valley of stability. Where's the neutron drip line? That is, how many neutrons can I keep adding on a specific species until my nucleus is not stable anymore? And how does all of it connect then to the description of neutron stars, for example? So those are our big questions. And in ab initio, we answer them, we try to answer them in a specific way. The idea with ab initio is Latin for from the beginning, from the very start. And so the very start is, of course, particle physics. You have quantum chromodynamics, you have your quark and your gluons, life is good, everything is fine. The thing is, once you try to describe your nuclei, so you have just protons and neutrons as meaningful degrees of freedom, well, you can't really use QCD. Lattice QCD for now is restricted to only a few nucleons. So you have to work around that. And the way we do it is with interactions that are anchored in a specific effective field theory of QCD that we call chiral EFT. I'll come to that in a second. Those interactions, so those Hamiltonians, we then use them to solve the A-body Schrödinger equation. We have our Hamiltonian, our wave function, and we obtain here, for example, the ground state energy, but all in all, a set of observables in a way that is hopefully consistent, like everything works together very well, systematic in our description of the nucleus, in our description of the interaction, hopefully accurate enough that we can meaningfully compare with our experimentalist colleagues. From internucleon interactions, we have no collective degrees of freedom as some of our colleagues who use other methods use. For example, everything is protons and neutrons and rooted in QCD through the particular symmetries of our effective field theory. So this type of method, they go way back. Actually, you could go back to the 80s, but they were for a very long time restricted to the bottom of the chart. You see a bunch of blue squares here. This is what we were able to describe from an ab initio method 20 years ago. And in the meantime, you see that we've expanded this thing pretty much to all the lower half of the nuclear chart here on the tin isotopic chain, and on a few here lead isotopes and surrounding, I think, and even more recently, it has been pushed even further to lead 266, if I remember the paper correctly. So that's what we're able to describe now. And a lot of this progress has been due to the use of expansion methods. So the initial, in a sense, ab initio method solved Schrödinger equation exactly, but that's super costly. You have a factorial or exponential cost. So what I and a lot of colleagues do is, well, realizing this is actually a very hard thing to compute, your fully correlated wave function psi. You start from a reference state, something more simple that we call mean field, phi, and you add what we call correlations on top. If you have an order by order expansion of those correlations, if you go to infinite order, wonderful, you solved exactly the Schrödinger equation. In practice, we did not do that. We stop after a couple of orders. From what you have left out, you might be able to estimate what is missing in the end. And since hopefully this order by order conversions work well, with only a few orders, you're able to grasp the most of the correlations and have a meaningful description of your nucleus. All of this gives you a controlled expansion of your method, controlled uncertainty, hopefully, and all of this at a moderate cost. Small footnote, some people have been able to reach mid-mass nuclei using other type of methods, and actually in this very building, the research group of Dean Lee, using nuclear lattice EFT. I will not talk about this method in the rest of the talk, but I just want you to keep that in mind. And now with the reach that we have today, and if I show the overlap with experimental facilities, the one that we have in France, actually Alto on our campus in Orsay and Spiral 2 at Ganil in Caen, these are the new area that they're trying to push for. And the exciting thing is you see that we already have some levels of overlap, and we're trying to fill as much of the gap as possible. So it's very exciting. And now new areas covered by facilities like FRIB or RIBF. You see that there as well, there is some overlap. There are new things that we are trying to push for. So we're already at the beginning of a new era of shared efforts with our experimentalist colleagues towards heavier nuclei, towards more exotic nuclei also. Exotic meaning most of the time, like going away from this valley of stability. And this is particularly exciting because for a long time, with the methods that we had, it was hard to give meaningful results to our experimentalist colleagues. This has been changing lately, and that's really a great thing for us. So now, in terms of what we have to do on a daily basis in nuclear physics, what we want, and especially in ab initio, is to determine certain observable O for certain synthane S with hopefully a precision level that we are able to estimate. And for this, you need a combination of roughly three things. You need a nuclear interaction, you need a many-body method, and you need to implement all of that in numerical codes. I will not discuss either many-body method or numerical aspects much in the rest of this talk, but I will focus on the nuclear interaction. And so I told you we use Chiral EFT as a model for our interaction. It's an effective field theory where the idea is that we have nucleons and pions as the meaningful degrees of freedom. And we want to exploit a separation of scale between the phenomena that we are trying to describe, which sit roughly at the pion mass, so 140 MeV and under or slightly above. And what we call the breakdown scale of our theory, lambda chi, which depending on who you ask is sitting at 700 MeV, 1 GeV, something like that. And by exploiting this separation of scale, you can build an expansion in powers of Q, so this low order over lambda. So you basically have a kind of Fourier expansion in the sense that gives you a natural hierarchy of terms. You know that you have some terms that will enter at leading order, some at next to leading order, next to leading order, and so on and so forth. And you see that those diagrams that have the nucleons as solid lines and pion exchange as dashed lines become more and more complicated as you move down this table. And this gives you a natural hierarchy of terms, but what is interesting for us is it also gives you a natural hierarchy of two-body forces, three-body forces, four-body forces, which is one of the specificities of nuclear physics, because we treat our nucleons, so our protons and neutrons, as point-like particles. We have three-body, four-body, etc. forces that emerge because they actually are not structureless. You have your gluons and quarks inside. So we have to deal with many-body forces, which makes the nuclear many-body problem particularly hard to tackle. The good thing, though, is with natural hierarchy of term, you have a systematically improvable description of the interaction. So the higher you go in this expansion, the lower you go in this table, the more diagram you incorporate. The closer you are to the true, in a sense, nuclear interaction. And so the lower the error you made on the description of your nuclear interaction. In practice now, the two-body terms, the nucleon terms, have been derived up to N4LO, though in practice, most interactions stop at N2 or N3LO. The 3N terms have been derived up to N3LO, though most of the interaction stops at the N2LO level, and nobody that I'm aware of is using four-body forces. So that's what we work with in practice. Now, some of you might ask me, okay, but what about the delta excitation? Well, here there's no delta excitation of the nucleon, but some colleagues work with a delta full representation of chiral EFT, and so then you get slightly different diagrams, small reshift, some diagrams are promoted to higher orders, things change slightly. I won't go into the details, but that will come in handy later on when we discuss actual interactions. And something that I want to discuss very briefly also is the leading contribution to the three-body force that appears at N2LO. So you have those three diagrams. You see that you have a two-pion exchange. It's associated to LECs, low energy couplings, that are set already in the NN sector. Those are what we call the CIs, C1, C3, and C4. But then we have two new LECs appearing with those two new diagrams, one pion exchange, two nucleon contact, and three-body contact term. And so those LECs, CD and CE, they have to be fitted in the three-body sector or above. Historically, they were mainly fitted in the three and four-body sector. And this three-body force, it's actually really important, not only from a conceptual point of view, but it has, in practice, a very important contribution. So those are predictions for oxygen, the ground state energy of oxygen isotopes with a bunch of different methods. The important thing is not here. The important thing is you see that you go down and then up again, which means that the drip line for oxygen isotope, the most neutron-rich bound oxygen isotope is oxygen 24. If you do this calculation with only two body forces, the line goes down. It keeps going down and down. You keep binding your oxygen, so you're not able to describe the physics of the oxygen isotopic chain correctly. Now, when you add three body forces, all of a sudden this works well. So this is really something that we need in practice. We cannot go around using three body forces. So after that, I want to give you a brief history of chiral interactions.
Yeah.
Mm-hmm.
Is it the case that the three-body force is more important than neutron system, or like on the oxygen shape? Nothing systematic.
I mean, I would guess so. I mean, basically the heavier you get, the more important the contribution is, and the more you deviate with NN only, you will deviate from the true results. Then is it a neutron-rich thing only, or is it just like a number of mass? I don't know actually. But yeah, that's the thing. If you do like helium-4, you can almost not use the three-body force, but when you reach the oxygen, you have to have it. And actually, if you play the game of doing NN only calculations up to very heavy nuclei, you see that the binding energy that you get per nucleon, you get to like 16 and above. So it's completely crazy as compared to the 8 MeV per nucleon that we typically get for nuclei. So yeah, we've been using chiral interactions for give or take 20 years. And if you read ab initio papers, you will see a number of acronyms, names that might be a bit hard to decipher. So the idea for me was to kind of walk through them, starting from the original, in a sense, interaction. The first one that was very largely used, the NTEM-Marlite 500 or EM500. Sometimes you will see it mentioned under just the name N3LO interaction. It was really a pioneering work where the idea was to reproduce the quality of phenomenological potential, that is AV18, CD bone, by focusing on a very good reproduction of the NN phase shift. The force was proposed as NN only, which meant it has to be supplemented with a three-body force that you added kind of ad hoc in a sense on top of it. It's still at the basis of a lot of the forces of the interaction that we use today. But the thing is, using this bare, and I'll come back to the meaning of bare interaction in a second, but uses this bare interaction with 3N on top. Very often, those forces fell short as soon as you move to medium mass nuclei, which in our language is calcium nickel isotopic chain, for example. So you see here in a paper we did with colleagues, including Heiko a few years ago, a bunch of ab initio many-body methods. Once again, the detail of those methods is not important. What is important is that you can see that they give very similar results, but you see that when we move from the oxygen isotopic chain to the calcium isotopic chain, all of a sudden we are overbinding with respect to experiment, to those black lines here. So this really shows that it's not a problem with our many-body method, it's a problem with the interaction. And also, this one is relatively hard interaction. That means it requires very large model spaces for our calculations to be converged, which means a lot of CPU time, which of course is not good. But this was really the first one in a sense. Then a few years later appeared this lambda family, and the most famous of them, the 1.8 2.0 EM interaction. The idea by the authors was to build on the success of the EM500 and to use SRG evolution on the NTEM-Marlite So I realized I forgot to include an SRG evolution slide. But the thing is, SRG is a similarity transformation, which is good because it means that it will preserve a lot of the physics that basically make our interaction softer. It decouples the low and high momentum degrees of freedom. So it makes the interaction softer, which means our interactions converge better. So it's good. The price that we pay is that through this evolution, you generate higher degree forces. So if you start from a two-body interaction, you will generate three-body force contributions that you have to take into account. At the time, it was not feasible. So what the authors did was SRG evolve the intermarlite two-body interaction. You throw away the induced three-body forces, and add a bare, so that is not SRG evolve in 3N interaction on top, fitting directly this three-body interaction at a relatively low cutoff lambda, fitting the CD and CE, and the name. The first lambda, the lowercase lambda, is the parameter for the SRG evolution, and the uppercase lambda is the cutoff, that is the limit above which our interaction stops. Is basically zero, to put it very briefly, and does not describe physics anymore. And so they saw this refit at low cutoff as a way to absorb the missing high energy, the missing three-body forces that were induced, this missing high energy physics. And the thing is, because this interaction was soft, it made for a very broad use. It was easy to use with many body forces. It gave very good results with energies, including excitation energies here for the calcium isotopic chain, for example. But the thing is, it underpredicts radii. So if you look at the manganese isotopic chain here, those are 2 neutron, if I'm not mistaken, or 1 neutron, I'm not sure anymore, separation energies. And you see that our blue dots are basically on the experimental results. But when you look at charge radii, you see that we're underpredicting them by, what is it, like 0.2, 0.3 Fermi. So that's the main deficiency of this interaction. Then another pioneering work a few years later, the N2LO SAT for saturation. The idea by Andreas Ekström and collaborators at the time was the interaction that we had that were fitted on in the 2 and 3 body sector underpredicted the radii. So they thought, okay, by including low energy many body data in our fit, probably we were able to reproduce the saturation properties of the nuclear interaction better, and so the radii better. At the same time, they did a simultaneous fit of all the LECs. This gave very good radii. Along with the radii, you can have a look at, for example, density profiles, and from that you can reproduce experimental cross-section. Here, electron scattering of xenon 132, for example, and you see that we reproduce the experimental results pretty well here as well. So excellent radii in associated quantities. It tends to slightly underbind in the AV sector, though, and it's really the interaction that pioneered the use of many-body data in our field. Roughly at the same time, a bit less popular, the N2LO SIM and SEP for simultaneous and separate. Here, the authors thought, okay, two-body, three-body sectors are equal only in name, usually in the fit of the interactions, because people will first fit the two-body sector and then adjust the three-body sector. So they wanted to compare strategies by doing separate, that is two-body sector first and three-body sector after, or simultaneous fit of the two and three-body sector. And especially the interesting thing that they did was looking at the correlation between the different LECs, low energy constants. So basically the parameters of our interaction, look how they are correlated. So this paper is still, I think to this day, a very interesting paper academically. Unfortunately, the interactions that were produced were underbinding already at the oxygen 16 level, so they were never really used a lot in in applications. More recently, the anti-Marlin-Nodzik interaction. So you take the same people as the old EM500, and they came back with always this focus on phase shifts using pionucleon scattering analysis data to fix the CI. But then this time the interaction was available at several chiral orders, from leading order to next to next to next to next to next to leading order. Still two body only, so it needs to be supplemented by a three body force. But this pioneered like detailed study of the convergence properties of nuclear interactions, because you're able to look at different orders of the chiral expansion. This was extended in different ways to the thorium sector, including by Thomas Hutter and collaborator. I told you some colleagues include explicitly the delta excitation. This is the case of those two groups of interactions, delta and 2LO GO, and the so-called non-implausible interactions. I won't go into the details here, but the idea from those two papers was to include the delta, study the convergence of delta full chiral FT with respect to delta less. Once again, using many-body data from the start of the process with interactions at NLO and N2LO. And this worked pretty well up to lead-208 neutron scheme. The non-implausible are a set of interactions, so that allows some form of uncertainty quantification, or rather that allows you to probe the physics sector that you can't really rule out, and it's non-implausible when you do nuclear physics. So they have good simultaneous reproduction of radii and ground-state energies, and a very encouraging order-by-order convergence, better than the delta less interactions. So maybe going delta full is actually the hope for the future for us. We shall see. And final one, if I remember correctly, the local non-local interactions that wanted to combine qualities of local and non-local regulators. I won't go into the detail. It's fit only in the few body sector. It's used a lot for spectroscopy of low mass nuclei. Works not too bad in the in the medium and heavy sector, but tend to underpredict radii. So your green curve here with respect to the black dots. And that was the state of the art a few years ago, when with Kai Ebler and Achim Schwenk, we started working on our own interaction, revisiting the low resolution approach that was successful with the 1.8, 2.0 EM that I introduced earlier. So the idea is to SRG evolve the NN force to 1.8 inverse Fermi, hence the 1.8, and then you take a bare three-body force and you fit it with a cutoff of 2 inverse Fermi. And so we wanted to revisit this approach and to obtain a good simultaneous description of binding energy and radii, and hopefully have interaction that work well from the light sector to heavy systems. So that is for us tin lead isotopic chains. So the first thing we did, or rather the first thing Kai did, was look at the Triton binding energy using FAD-AF method and obtain a bunch of curves. I want you to focus at first to the left-hand side panel. What you see are a bunch of curves for interaction, the N2LO SIM with different cutoffs ranging from 450 to 550, the anti-Marlin-Nodzik 450 and 500, and 2 interactions by Evgeny Yepelbaum that weren't never really used for application. And those curves give you the values or the sets of values of CD and CE that reproduce the Triton binding energy for bare interaction. So you see that you have this parabolic curve that the higher the value of the cutoff that you get, the more parabolic the curve is. And then if you move to the right-hand side, those are the same interaction, but that have been 1.8, 2.0 IFI'd in the sense. So we play this game of SRG evolution, low cutoff, and all of a sudden you see that you obtain pretty much straight line, so quasi-linear relationship between CD and CE, and a very mild dependence on the original LECs. You see that the different EMNs, they're basically on top of each other. The N2LO seams are very similar also. So that means that's a sign that the interactions that we obtain through this are very perturbative. And then this set of associated CD and CE values, we use them. So here you have for oxygen-16, the ground state energy and the charge radius for 1.8, 2.0 interaction for different values of CD. And so implicitly for the associated values of CE I showed you on the previous slide. You see that for the binding energies, the EMNs tend to stay a bit away from the experimental value. They work in a sense only at very negative CD values, while for the N2LO seams and the 500, we stay close to the ground state energy in all of the positive domain. This empty star here corresponds to the old 1.8, 2.0 EM interaction value. And the interesting thing for us was looking at the charge radius at the same time. You see that if you take, let's say, CD 7.5, you obtain pretty much the experimental charge radius of oxygen-16. You're not too far away from the ground state energy. So we thought, okay, let's take the M500 and the SIM 550, take this value of CD 7.5 and see how it looks for heavier nuclei. So you have the binding energy of ground state energy rather scaled by the number of nucleons, charge radius scaled by h to the power of 1/3 for a set of doubly closed shell nuclei ranging from oxygen-16 to lead-208. And we wanted to compare to two interactions that have been pretty successful, the 1.8, 2.0 EM and the delta N2LO GO. So that was the state of the art in the field, and with our two new interactions, that's what we got. So you see that we have a very reasonable reproduction of experimental values for the binding energies. As soon as we move to calcium isotopic chain, we're never too far. We basically are as good as the others. But the big change is for the charge radii. By just including oxygen-16 in our data, we basically go through the experimental points for all the other systems. So we have an excellent combined reproduction of charge and charge radius and mass. So we are happy. We are very happy about that. And at this time, we are discussing with experimental colleagues in Darmstadt, the group of Thomas Aumann working on R3b at GSE. And they were doing neutron removal of tin isotopes as a way to access the symmetry energy slope L for nuclear matter through the cross-section. But the thing is, this cross-section, it's also correlation in L. They're also correlated to the neutron skin. So to put it briefly, the difference between the neutron radius and the proton radius of the nuclei. So since this is L is correlated to the neutron skin too, we thought, okay, that's a great test case for our interactions. So same set of nuclei, same set of interactions compared to experiment. And two very surprising things for us. One, we actually have a very good reproduction of the values that are known. Lead-208 is a bit of a controversial one. You see that the experimental values are very different depending on the method you use. But we are very happy about this reproduction. And the other, even more surprising thing to us was that even the interaction that underpredict the charge radii, right, the 1.8, 2.0 EM and the delta N2LO GO, they give the same reproduction, the same value as our two new interactions. So there seem to be, in chiral interaction, this strong constraint on neutron skin, on the isovector properties that was a news to us. So since we were looking at tin 120, among other things for collaborators, we looked at density profile, so the charge density distribution and the point neutron density distribution compared to, once again, the delta N2LO and the N2LO sat, which is an interaction that we knew give good densities. So you see that for the charge one, the experimental description is 2-point Fermi or 3-point Gaussian. So we can't really go into too much detail of what happens inside, but all of those interactions work pretty well. The picture is pretty good as well for the point neutron density distribution, with maybe the GO giving a slightly better reproduction of the surface, extending slightly larger. But another good thing was that the uncertainties associated to our model space convergence, so basically the thickness of those bars, those uncertainties were very moderate, which was a good sign. So we thought, okay, can we go even heavier to lead to weight? And actually we can, and we reproduce pretty well this compilation of results from Froid and Papa Nicola, except at the very center of the nucleus, but that's where we have the most uncertainties linked to our many-body convergence. So we are pretty happy. We have interactions that are consistent over the whole nuclear chart. That's a good thing. And so after that, we moved back to the neutron skins and thought, okay, since neutron skins are associated to protons and neutron densities, those things evolve along an isotopic chain. You will get quite intuitively a larger neutron skin, and actually the liquid droplet model, so old phenomenological model, actually predicts a quasi-linear dependency between the neutron skin and what we call the isospin asymmetry, n minus z over a, that we call I in the rest of the talk. And such linear dependence was confirmed recently by ab initio colleagues using coupled cluster and Monte Carlo methods, some Novario and collaborators. But for relatively low mass nuclei up until mid mass, but not very heavy. We thought, okay, in our case, we can go very heavy. So what does it look like? So we computed for all subshell closed oxygen, calcium, nickel, tin, and lead isotopes that we could compute the neutron skins. And here it's plotted with respect to I. And what is plotted is actually not quite the neutron skin, but the difference of the neutron skin of a specific isotope with respect to the symmetric L equals Z isotope of this isotopic chain, which is basically an effective way of dealing with the fact that the Coulomb repulsion makes your proton density slightly larger within the nucleus, and which is also the reason why you see all those points line up perfectly with the origin here. And so you see a couple of things. First, in a first regime, you see that all our interactions, but also all our different nuclei lie pretty much on top of each other up to I equals 0.2, 0.25. And then all of a sudden, the thing expands. So you have more difference between the different isotopic chain, but also, and this is very visible on this inset of the different nuclei that are at I equals 1/3, you also have more difference between the different interactions, which is interesting because those very neutron-rich nuclei are becoming more reachable with the new RIB facilities that are opening up. So that's very exciting for us, and that gives us good opportunities to discuss with our experimental colleagues. We think those are good physics cases to explore. And as a short side note, we saw also a strong correlation of the neutron skin, or when I say we, it's Nicolas Koak, who was a bachelor student in Darmstadt, working with Achim and myself, showed a strong correlation of the neutron skin also with the charge radius, mirror nuclei difference. So the difference of the charge radius of two mirror nuclei. So when you inverse the number of protons and the number of neutrons, it's a bit of a mouthful, but really a lot of interesting physics to look at behind those neutron skins. Very briefly, very preliminary results that I want to show, also to show how we can meaningfully discuss with our experimentalist colleagues. The group of Zeni Rosan worked in RIKEN on proton scattering to extract the matter distribution of tin 132, an approach that is complementary to the usual electron scattering that you use to extract the charge distribution. The experiment was run at RIBF using big ribs. And basically, we give them charge density, but also matter density distributions with or set of 4 interaction. And from that, they reconstructed the differential cross-section, and you see that we have a very reasonable reproduction of their experimental results, which then translates in terms of matter radius here and charge radii here in this slightly densely populated plot. You see here in red the matter radius that they extracted with uncertainty. Here in blue, the charge radius value from Isolde at CERN. Here, a bunch of different energy density functionals, so another type of nuclear many-body method. And most of our interaction, and sitting here, hidden behind the red bars, is the delta into LOGO result, which gives slightly smaller charge radii, as you would expect, but that also means slightly smaller matter radius with respect to our other interactions. And with that, I come to my conclusion. So I've mentioned many methods that are now a staple of nuclear physics, offering a systematic approach to nuclear structure and reactions, which I've not talked about, but is the subject of my visit here in FRIB. Tremendously improved reach in mass and number of observables that we can tackle over the past 2 decades. It's a very active field of research connected to other communities in nuclear physics, in astrophysics, but also in quantum chemistry, for example. I've introduced 2 new interactions that are accurate over the nuclear chart with good convergence properties, good simultaneous production of energy, radii, and neutron skins. And I've talked a bit more about the neutron skin dependence on isospin and the physics that we can discuss with that. And with this, I thank all or almost all, I realized I missed 1 or 2 this morning, past collaborators and you for your attention. Thank you.
Any questions? Indeed.
Okay, I have a couple. First one is that throughout the it tends to be to magic and doubly magic nuclei.
Yes.
So is there a reason for that? Are we only good at doing that, or
can you repeat the question, please? So that
Okay, yeah. So Andy was asking why in most, if not all the presentation, I was sticking to singly and doubly magic nuclei. The reason is it's easier, and even historically, and that's why if I move back to the nuclear chart, you will see that we fill up. It's more visible in the 2015 one. We fill up the magic shells before we are able to reach like doubly open shell nuclei. From the point of the thing is, this requires most of the time, or this requires more sophisticated many-body methods, which also means more computing time very often, because basically you kind of have 2-way. Tackling closed shell nuclei is very easy, but when you have open shell, that means basically you have some level of degeneracy, which means that you cannot play the particle hole excitation game as easily as you used to. So the community works mainly with 2 ways of circumventing that problem. Either you break a certain number of symmetries. That means you take a more sophisticated reference state mean field phi. But then your calculations are more complicated. That also means you ideally need to restore the symmetries, which is also something quite complicated. The other way to go around that is to, which was something that was introduced, that was very successful with IMSRG, for example, was the valence space in medium SRG, introduced by Ragnar Stroberg and collaborators a few years ago. And then the idea is to use your many-body method as a way to generate, to evolve, in the case of IMSRG, operators that you then put in shell model codes. So our phenomenological shell model colleagues, they have decades and decades of expertise. They've built super efficient codes that work very well, that also can tackle a very large range of observables. So in that case, you use your ab initio many-body method to generate operators that you will plug into a shell model code, and that's basically the type of method that has been useful to fill this bottom of the chart. So yeah, usually it's easier to start with the closed shell nuclei, but I can show you open shell results after if you want.
Thank you. I have questions, but.
Could you just go back and get a little bit more detail on like the workflow of the 1.8, 2.0, starting from a bare action or bare interaction? What do you have to do to get a full?
Sure. So Kyle was asking about the 1.8, 2.0 workflow and how it works. Yep. Yeah, that would be that one. So you start from this NN force. So if you play the game with the EM, it's the EM 500 in the two-body sector, and you SRG evolve it. You SRG evolve it only in the two-body sector, which means that implicitly you're throwing out what are the induced three-body forces. So in the two-body sector, you now have an interaction that is softer, that is more diagonal. If you think in terms of our matrix representation, where you have the value of your matrix element as a function of your relative momenta, so that makes the force more diagonal. And because SRG is a similarity transformation, that means that one of the things that you preserve are the phase shifts, which is something we're very interested in. And then you take a three-body force. I didn't say that, but the approach that was originally chosen and that we kept in this new paper was the three-body force. We take all the LECs that have already been fit in the two-body sector. We keep the same values. So that gives you only the CD and CE that you need to fit. And then the choice is to do that at 2 inverse Fermi, so that's 395 MeV, which, as you see, is smaller than the typical interactions that we use, which are between 450 and 550 is pretty rare, but that still happens. And so this idea of this low cutoff is kind of to put it on par with the fact that you have SRG evolve the NN sector, you have a low resolution interaction. And in the refit, the idea is that hopefully you absorb some of the physics from the induced three-body forces that you threw away. In practice, it seems that it doesn't work too badly, and there are good physics reason for that, because it's the same type of physics that the CDC are describing and that you threw away, etc. But there's no a priori obligation for this to work. In practice, it seems to not work too bad. And so yeah, so for this fit of CD and CE, the original 1.8, 2.0 EM used the triton binding energy, as I've shown, and the helium-4 radius. And here we kept the triton binding energy, but we shifted to the oxygen C16 radius, with fit being having a very broad exception in the sense that I use it. Like we do not try to reproduce exactly the values have you seen. We just want to be in the ballpark of the actual experimental value.
So how does that fitting procedure actually work?
I mean, Kai obtains these trajectories that reproduce the triton binding energy for CD and CE. And then we just picked a set of different CD values. And so to each CD value, you have to go back to this curve right inside. You have to go back to this curve and pick the CD that is associated to that. So implicitly here hidden, there's also a specific C value. But here we just picked not completely random, but a certain number of values. And it turned up that 7.5 was like on top of it. But yeah, as you see, one of the stars is slightly under, one of the stars is slightly higher. So we want to have a reasonable reproduction, but we do not reproduce the charge radius of 16 to 3 digits or
So
whatnot.
it would be, so you're fitting to like triton binding energies, and then you're sort of hand picking
Yes,
something that's consistent with oxygen 16. Okay,
exactly.
thank you.
Patrick,
On slide 15, you talked about the fitted simultaneously and separately, and their fits are different. So I guess that means that the three nuclear force is not charged in these bits. Is that the right interpretation?
Yes, I mean, one of the things specifically that was interesting is they discuss also the fitting strategy. They went like order by order. I think also like they have an LO and N2LO, if I remember correctly. And basically by playing the exact same game simultaneously and separately, they also discuss the fact that if you do the things separately, you have local minimas that appear and that you might get trapped into that do not appear if you do the whole thing simultaneously. But yeah, in a sense for us, like we'll always like derive the NN and the 3 and 4 the expressions that are prior, and then it's just a matter of setting all at once or in different steps the values of the different LECs. So as you have guessed, like this correlation plot, this corresponds to the simultaneous fit, because historically what was done was do first the NN sector, so that's I mean actually NN and also pi-nucleon sector, so that would be those two big squares, and then do the 3-body sector completely independently. So which would put all those of diagonal values here to 0. And actually they show that here you have some level of crosstalk in a sense between the 3-body sector and the 2-body sector that just didn't exist prior to that, because like these forces, and especially the N2LO SAT before, they led to a kind of shift of paradigm and mentality within the community, which I didn't really discuss, which was that before people saw ab initio also in a very strict sense, also in the fitting procedure, that, okay, you fit the 2-body force in the 2-body sector because you don't want to put like 3-body physics into your 2-body force. And then your 3-body force, you fit it in the 3 and 4-body sector because you need to go to 4 very often because we're lacking data. And then the 4-body force would be fitted only in the 4 or 4 and maybe 5th-body sector, etc. With that, and at the same time, the SIM SEP, but as I was telling, like those were not as popular, but it's still a very interesting academic paper to read, I think, if you're interested in interactions. There was really this fit with two simultaneous fit actually work great. And it's not a matter of like not putting many body data into our interactions, but the key is that we have a low energy effective field theory, so we should use low energy data. But there's no reason to exclude using many body data in our fit, because what the key is low energy and is not just like fitting only in the 2 and 3 body sector.
Yeah, I mean, I actually have a different question, but first you confused me considerably on 22 when you talked about the induced three body forces and true three body forces. Because from some people, I understood you have to take in the induced. Once you do a many body calculation, you take into account the induced three body forces and then plus the true three body forces. You were just saying you don't do that.
Okay, so the question of Charlotte is to clarify the induced versus bare three body forces and how we do things. So ideally, if you use SRG, right, you start your NN, 3N, and 4N forces, and you have those forces, and when you SRG evolve them, you get another set. Actually, I should fill those ones, and have those ones be empty. You get new set, and basically you have this combination of a part of the three body that comes from the evolution of the bare three body, and a part of the three body that comes from being induced by the evolution of the two body, right? In this case, we do not play that game, so we throw away. I mean, we have no four body in the first place, but you do not take into account what is induced, which was originally at the time in 2011, because they just did not have full 2 and 3 body SRG code. Like, this is still pretty expensive to run today, but this was just not feasible 14 years ago. So the idea is that since you don't include the induced, the 3 body that comes from the SRG evolution of the 2 body, to effectively, in a sense, include it by fitting this bare interaction on top of the SRG evolved two body with this low cutoff of 2.0. I'm not sure I've made myself clearer.
What you get, the cutoff plus the C's are then effectively containing in principle evolved three body forces plus genuine, and you kind of get this, you sum it up in some effective CDs. Some people have made this big thing that they are that the constant have to be consistent in all places, but you so the way you are doing it, it looks to me as if you have an effective CD and an effective which contains some.
In a certain sense, yes. And for example, like, I regularly have people asking me, like, tell me, okay, you have a very large CD that's unnatural. And I'm like, yes, but this is, I do not say that this is the true physical CD, if that even makes sense, because then we can talk about the fact that with SRG, you can rehash, if you do it consistently, you can rehash everything. And so what is an actual value of an LEC in the first place? But this particular value of CD is very probably a testament to the fact that we follow this procedure and that we have this fit at low cutoff already. And this is actually to some extent visible in in the paper of Thomas Hutter and collaborator, where they did things differently. So in their case, it's consistent SRG evolution of the EMN interactions, but it's consistent with SRG evolution, but they fit to oxygen 16, and they play this game at different values of cutoffs. And you see that the lower the cutoff they have, the larger the value of CD, and it's relatively dramatic. Like, I think if I remember correctly, for 550, for a cutoff of 550 MeV, they have CDs of like 3 or 4, something like that. And then moving to 450, they get a CD of 9 or 10, something like that. So I think those large values really show the effective resumming of higher momentum, higher energy interaction into the whole SRG plus low cutoff procedure.
Okay, we're on top of the hour. I will allow one quick question, and then if you have more, Pierre is here. His office is, I don't remember the number.
2118.
2118, excellent. So it's across from the coffee machine on the second floor. That's here. Okay, any quick questions? Chile, please.
Yeah, so when you compute the charge radius, after you do SRG on the interactions, do you also transform the density operators?
Okay, so the question of Shilin is consistent evolution of the other operators for charge radii, for example. In that case, no. Like it's really the SRG evolution is really there to produce our interaction, and after that we do everything as if it was a bare interaction. So we have the SRG in the sense the IM SRG evolution of the operators, because I did not discuss the many-body aspect, but the results I show are IM SRG2. So within the IM SRG, there's the evolution of all the operators, obviously. But once with the SRG we've produced our Hamiltonian, then we use our interaction as if it was a bare interaction. We do not evolve separately the radius operators or other operators.
So do we worry about two-body current operators can be used?
That's something, you're not the first one asking that. We have absolutely not looked at the currents, so I have no idea. But yeah, that's something that we have to look at, especially people also pointed that with those large CDNC values, and this is related to current operators also, and that could be a problem. We haven't looked at that yet.
Okay, good. Let's thank Pierre again.